Hello everyone, I'm Afroz Javalameli, and in this video I present our paper about the skewed strip packing problem. This is a joint work with Waldo Galvez, Fabrizio Grandoni, Klaus Janssen, Arlindam Khan, and Malin Rao. We begin by introducing the problem formally. In the strip packing problem, as an input, we are given a strip with width W and infinite height. We assume that W has integer value. So here in this example, the strip is shown on the right. We are also given a set of n rectangular items, each of which associated with width wi and height hi, which we assume that wi and hi are integers. We also assume that wi is less than equal w. This is because we want to have the condition that any rectangle can be placed inside the strip without needing any rotations. The objective is to find the feasible packing, or shortly packing, of the items in the strip with minimum height. By a packing of the item inside the strip, we mean a placement of the items inside the strip such that they don't intersect. And the goal is to minimize this value h. This indeed has many applications. For example, in many industrial purposes, the goal is to produce rectangular pieces out of the raw materials. The raw materials, however, are usually given in the form of rolls of constant width and different lengths. Being able to do this with rolls with a smaller length helps the manufacturer in terms of cost of the raw materials and prevents the waste of material. Another application for this problem is in the energy management purposes. Here we deal with appliances that consume energy, and each of them is used in an interval of time with fixed duration length during the day. The goal is to assign a starting time for each appliance such that the peak energy consumption minimizes. We can assume that each item is a rectangle with width equal to its duration length and height equal to its energy consumption per unit of time. Now we can use strip packing to approximate the minimum possible peak. The state of the art of this problem is as follows. So strip packing is known to be 3½ minus epsilon APX hard. This can be shown by a simple reduction from the famous partition problem. Then there were a long sequence of improvement in terms of the approximation factor for this problem. The first algorithm designed for these problems were in 1980. There was a 3 approximation at that time by Baker et al. And a 2.7 approximation by Kaufman et al. Then this was improved to factor 2 with 2 independent papers, one by Steinberg and one by Schiermeier. And then it was stuck on the barrier of 2. And then Haren and Vanessy managed to break the barrier in 2009. And finally, Haren, Janssen, Pradel, and Vanessy obtained a 5^3+epsilon approximation factor for this algorithm, which is the current best status of this problem. So now there is this open gap from 3½ minus epsilon to 5^3+epsilon. In terms of pseudo-polynomial time approximation algorithm, the situation is slightly different and the case is almost closed. Note that by pseudo-polynomial time algorithms, we consider the algorithms that have running time polynomial in terms of n, w, and h max, where h max is the maximum height of the items. In terms of hardness, there are 2 results. The first one is a 12/11 minus epsilon APX hardness result by Adamowczyk et al. And the second one is a 5/4 minus epsilon APX hardness result by Henning et al. In terms of approximation algorithms, there were improvements from 3½ epsilon to a 5/4 epsilon. This 5/4 epsilon is a result by Janssen and Malin Rao, which was recently presented. So now you can see that the case is almost closed, and the only question left here is that does there exist an approximation algorithm with factor exactly 5/4 or not? A general approach to attack this problem is to classify the items by size. Consider mu and delta to be constant values from 0 to 1 such that mu is smaller than delta. Also assume that T is an upper bound on opt such that T is less than equal 1 plus epsilon opt. Now for each item I, the height can be classified in, their heights can be classified into 3 groups. The first class is when the height is at least delta t. So in this case, we say that the item has a large height. Or the height stands between delta t and mu t, which we say that the item has medium height, or the height is less than mu t. In this case, we say that the item has a small height. The same can be done for width in terms of w. And now we can combine these two classifications together to classify the items by size. For instance, if the items has large width and large height, we say that the item is large. If the item has large heights but small width, we say that the item is vertical, and so on. One can observe that there can be only constantly many large items in a strip packing instance. And all the possible packings of these items, therefore, can be enumerated in constant time. So this suggests that in the strip packing problems, most of the hardness comes from the other items. So if we are given an instance containing only large items, now we are even able to compute it efficiently. But does this hold for the complementary case? Now we describe the complementary case formally. We say that an instance of strip packing is delta skewed if for all the items we have this property that either the width is less than delta w or the height is less than delta t. So this means that in the classifications of the items before, we have no items which stands in the large items category. Our result for this problem is as follows. We show that the hardness for the strip packing problem is still holds for the delta skewed case. So we basically show that this problem is also 3½ minus epsilon APX hard. We also present a 3½ plus epsilon approximation for the delta skewed problem. So combining this with the hardness, we get an almost tight result. Now we present our hardness result. We use a reduction from the partition problem, which is a well-known open problem. Consider an instance I of the partition problem containing n positive integer numbers a1 to an such that the total sum of these numbers is exactly 2s. Note that in the partition problem, we have to decide whether it's possible to partition these numbers into 2 sets such that the total sum of the elements in each set is exactly s. From this, we can construct an instance J of delta skewed strip packing problem as follows. First, we set the width of the strip to be 1 plus 2 over delta times s. Now we construct the items as following. We set the height of all the items to 1. Then for each I from 1 to n, we introduce an item of width ai. We call these items the main items. We also introduce 2 over delta items of width exactly 2s. We call them the dummy items. Note that the width of any items in J is less than delta w, which guarantees that we have a valid instance of delta skewed strip packing. An important observation here is that any solution of J with non-integer objective value can be transformed in polynomial time to a better solution in terms of objective value, such that the objective value is an integer value. The reason for this is that if you consider any item in the strip, you can push it down until either it touches the bottom of the strip or it touches the top edge of another item. So using this, now the bottom of every item is placed in an integer value, and since the heights are integer, so the top of every item is also placed in an integer value height. Another observation is that since the total area of the items is exactly 2 times w, then the optimal value for J is at least 2. And because of the previous observation, so now either the solution, we have a solution of size 2, or the solution has size at least 3. We show that there exists a solution of size 2 for J if and only if I is a yes instance for the partition problem. Now assume that I is a yes instance for the partition problem. Now we can partition the set of main items into two subsets, S1 and S2, such that the total width of the items in each subset is exactly S. Now consider the sub-area of the strip formed by limiting the heights from 0 to 1. So this rectangle here is the sub-area that we are discussing about. We call this the bottom shelf. Also consider the sub-area formed by limiting the height of the strip from 1 to 2. We call this rectangle the top shelf. Now we show that one can place the items in S1 in the right of the bottom shelf and then 1 over delta dummy items and to the left of these items and place the rest of the items in the top shelf. Here in this instance, you can see that the dummy items are shown by light gray and the main items are shown by dark gray. Now assume that we have a solution of height 2 for j. Then since the height of the items is exactly 1 and their total area is exactly 2 times w, then the items must be partitioned into two subsets such that the first subset is completely contained in the top shelf and the second subset is completely contained in the bottom shelf. And the total sum of the widths of each subset is exactly w. Since we cannot have more than 1 over delta dummy items in each shelf, then the main items in each shelf have total width of at least s. So this means that I is a yes instance. This shows that the strip packing cannot be approximated with factor 3½ minus epsilon unless p is equal to np. In this section, we describe our approximation algorithm. First, we explain the general approach of previous algorithms with a more focus toward the approximation algorithm of Hardness et al. These approaches begin by transforming the optimal packing to a packing with simple structure. In the literature, this is mostly known by the structural lemma. In order to obtain a structural lemma, two things must be done. The first thing is to partition the packing into constantly many sub-areas. And then the next thing is to shift and reorder the items inside each sub-area so that the packing in each sub-area has a special structure. Now, having this structural lemma in hand, we can efficiently compute packing which is almost optimal. The first thing is to iterate over all structure to find the best structure possible. Note that since the number of sub-areas are constant, so this doesn't take much time. The next thing is to place almost all items using linear programming or dynamic programming inside the strip without going above the height of 1 plus epsilon opt, where opt is the height of the optimal solution. And by almost all the items, we mean that we are only allowed to discard a subset of items containing epsilon fraction of the total area of the items. Recall that in the strip packing, we must pack all the items, thus we have to add the discarded items. Thus we need an extra rectangular subregion to pack those items. This extra rectangular region is of height opt and width epsilon w in the paper of Hardness et al. Here it's easier to understand this approach, so consider an optimal solution here. And now we want to prove a structural result for that. First, you can see the classification of the items. So for example, the green items, the light green items are actually the vertical items and the dark green items are the large items and so on. You can see the vertical items in purple and the orange items are the small items. So you can see that the vertical items are together and they are contained in a big vertical and rectangular area. This also holds for the horizontal items. They are contained in a horizontal region, and also the small items are together in a rectangular area. The main thing is to first obtain these subregions. These subregions in the literature are mostly known as containers. So once you find these containers by iterating over all the possible structures, the next thing is to try to pack as much possible of the items inside these containers. Here you can see that almost all the area of these containers is filled except for a small amount. Then they show that in order to pack the remaining of the items, having two extra boxes is enough. One box is basically a rectangular region of height opt and width epsilon w, and another one is a rectangular box of height epsilon opt and width w. Note that the horizontal box, it does not affect the optimality of the solution that much, since its height was epsilon opt, but the second box is actually problematic, the vertical box. The novelty of the work of Haran et al. Was that they were able to rearrange the items in the packing such that they could place this vertical box without going above the threshold of 5/3 opts. Our strategy is somehow different from the approach of Haran et al. The key idea is that we place all the items with height larger than opt-half inside the structure solution. Now the unpacked items have height less than opt-half, which results that additional container only needs a height of at most opt-half. Recall that for the approach of Haran et al., this extra container had height opt. We also use a specific classification of items according to their sizes. The first class is the class of tall items, which are the items of height at least opt-half. We denote them by T, and in the figures we label them by the color orange. The second class of the items are the vertical items, which have height less than opt-half but more than delta opt. We denote them by V and color them by green. And the rest of the items are the short items. We denote them by S, and their color can be recognized in the figures by purple. The first step is to obtain a structural lemma and generate the structured packing. We begin by an optimal solution, a solution of height opt. The items are classified according to their sizes, as you can see in this figure. Now we only consider the tall items and the short items. We slice the short items horizontally to obtain slices of unit height. Now consider the horizontal line at height opt-half. The slices are either below opt-half or above this height. Next step is to move all the slices which were below the height of opt-half by opt units so that they go to this sub-area. Now we shift down the tall item so that they touch the bottom of the strip. Now we shift the tall items to the left and sort them according to their height. We also shift the slices to the right. The next step is to shift up the stripes and sort them according to their sizes. Now the silhouette of both item sets, they form steps, as you can see. We shift the slices up by O epsilon opt units. So now the height of the solution increases to 3/2 plus O epsilon opt. Then we round up the silhouette so that they have constantly many jumps. Then by drawing the vertical lines from the corners of the silhouettes, we obtain these rectangular sub-areas, which we use them to pack the vertical items. Note that the total area inside these containers is at least the total area of the vertical items plus 1/2 plus epsilon times W opt. So now we can pack the slices of vertical items inside the containers greedily since their height is less than opt-half. Also, we guarantee the existence of free area with width omega epsilon W and height opt-half. Till now, we were able to prove the structural lemma. Note that the slices of the short items were placed inside the horizontal containers, and the slices of the vertical items were placed inside the vertical containers. Now we use a standard technique to obtain the packing of the original items inside the containers. So assume that we are given a set R of constantly many rectangular regions, and we have a set of items I with the following properties: that the slices of the short items in I can be placed inside the horizontal regions of R. Also, the slices of the vertical items can fit inside the vertical regions of R. And the height of each horizontal region is sufficiently larger than the height of the short items, and the width of the vertical regions are sufficiently larger than the width of the vertical items. And by sufficiently larger, we mean by a factor 1 over gamma, where gamma is a fixed constant. Then we can pack integrally almost all the items inside the region. And by integral packing, we mean a packing of the original items without allowing its slices. And by almost all the items, we mean that the area of the discarded items is very small. And by very small, we mean that the area of the unpacked items can be bounded by O of gamma times the area of the total area of the items. Here you can see two containers. The container in the left is a horizontal container containing the horizontal slices of the short items. The container on the right is a vertical item containing the vertical slices of the vertical items. Now, if we want to obtain an integral packing from the packing of the slices, we need to discard some of the horizontal items and some of the vertical items. So we need two extra rectangular regions, a horizontal region for packing the discarded horizontal items and a vertical region for packing the discarded vertical items. The important thing is that this vertical extra box can be placed inside the free area we introduced in the structural lemma. At this stage, I would like to give a short summary of the algorithm. We start by placing the tall items at the bottom left of the strip and sort them according to their heights. Then we guess the containers for the horizontal item, and using them, we can generate the containers for the vertical items. Now, using the standard technique described in the previous slide, we can place almost all the horizontal and vertical items inside the containers. Note that if we made the correct guess of the containers, then the items fit inside these containers, allowing a slicing. And finally, for the discarded items, we need an extra horizontal box, which we put it at the top of the strip, and an extra vertical items, which we can place it inside the free area that we guaranteed in the structural lemma. Recall that in this video, we introduced the delta skewed strip packing problem. Then we presented two results for this problem. The first one was a hardness result. We showed that this problem is 3½ minus epsilon APX hard. Then we presented a 3½ plus epsilon approximation algorithm for this problem, which is an almost tight approximation algorithm. I would like to end this discussion by proposing three open problems. The first open problem is the main open problem in this area. Can one improve the approximation factor for the strip packing problem from 5/3 plus epsilon? Note that one cannot hope for an approximation algorithm of factor less than 3½. Another way to attack this problem is to improve the lower bounds in terms of approximation factor. So the question here is that does there exist a better hardness result? And by better, we mean better than 3½ minus epsilon for this problem. Another open problem is that to find another classes of items or another combinations of the classes of items that one can obtain a 3½ plus epsilon approximation algorithm for that. For example, in this paper, we considered all the classes of items but the large items, And what we think that it might be interesting is that instance containing only large and vertical items. Thanks for watching this video.